Deep in the Gobi Desert, China is running an experiment that could change one of the most important technologies on Earth. It is not the biggest reactor ever built. It is not even close. The machine produces just 2 megawatts of thermal power, but what happens inside it is the part that matters. Instead of relying on the conventional nuclear fuel system used by most reactors, this experimental machine uses molten salt, operates at high temperature, and has been loaded with thorium. And in 2025, Chinese researchers reported something they had been trying to prove for years. The reactor successfully converted thorium into uranium, demonstrating the key step in a thorium fuel cycle. That does not mean China has ended the energy crisis, not even close. But it does raise a much more interesting question. What if the nuclear reactor of the future does not look anything like the nuclear reactors we have been building for the last 70 years? Because this tiny machine in China's desert may be testing exactly that idea, the problem this reactor is trying to solve. The world's energy problem is not simply that we need more electricity. We need more electricity that is available when we need it. That distinction is becoming increasingly important. Homes are becoming more electrified. Cars are becoming electric. Industries are replacing fossil fuels with electricity wherever possible. Data centers are consuming enormous amounts of power, and the growth of artificial intelligence is adding another layer of demand. At the same time, countries are trying to reduce their dependence on coal, oil, and natural gas. Solar power can produce enormous amounts of electricity. Wind power can do the same, but the sun does not shine every hour, and the wind does not blow on command. That means an energy system built heavily around renewable generation also needs storage, transmission, flexible generation, or some combination of all three. And this is where nuclear power becomes interesting. A nuclear reactor does not need sunlight. It does not need a windy afternoon. It can produce heat continuously, day and night. But conventional nuclear power has its own problem. Building a giant nuclear plant is an enormous engineering project. You need massive infrastructure, highly specialized components, extensive safety systems, strict regulation, and years of construction. And the reactor itself is built around an architecture that has changed far less than most people realize. Solid nuclear fuel, water or another coolant, high-pressure systems, steam, turbines, electricity. The basic concept works. In fact, it works extremely well, but the question China is asking is different. What if you redesign the reactor around the fuel itself? What if the fuel were not locked inside solid rods? What if the coolant could operate at atmospheric pressure? And what if a different element, one that is far more abundant than the fissile uranium normally associated with nuclear power, could become part of the fuel cycle? That is where thorium and molten salt reactors enter the story. And that is where China's experiment becomes much more interesting than its size suggests. Why conventional nuclear power is so complicated. To understand why this reactor matters, you first have to understand what it is trying to change. In a conventional nuclear reactor, the fuel is solid. Uranium fuel is manufactured into pellets. Those pellets are placed inside long fuel rods. The rods are assembled into fuel assemblies and placed inside the reactor core. When uranium atoms undergo fission, they release enormous amounts of heat. That heat turns water into steam, and the steam drives turbines that generate electricity. It is a proven system, but there is a fundamental engineering challenge. The reactor is producing an enormous amount of heat inside a solid core, and that heat has to be removed continuously. The coolant has to keep flowing. The pumps have to work. The systems have to remain within carefully controlled temperature and pressure limits. And in many conventional reactors, the primary cooling water operates under extremely high pressure so that it can remain liquid at high temperatures. That pressure is one reason the containment and cooling systems are so complex. Now imagine taking one of the most important assumptions in that system and throwing it away. Instead of solid fuel rods, imagine putting the nuclear fuel into a liquid, not water, molten salt. At reactor temperatures, the salt becomes a liquid capable of carrying both heat and, in a liquid fuel design, dissolved nuclear fuel. The reactor then becomes something fundamentally different. The fuel is moving through the system rather than remaining permanently locked inside solid rods. That does not magically eliminate every nuclear engineering problem. In fact, it creates some entirely new ones. But it also opens the door to a different architecture, and China has spent years trying to prove that architecture can actually work. The small reactor in the desert. The machine at the center of this story is called TMSR LF1. It was developed by the Shanghai Institute of Applied Physics, part of the Chinese Academy of Sciences, with other Chinese institutions. The reactor is located in Wuwei, in China's Gansu province, and its size is almost misleading. TMSR LF1 is a 2-megawatt thermal experimental reactor. It achieved first criticality on October 11, 2023. Then, on June 17, 2024, it reached full power operation. So this is not a hypothetical reactor sitting inside a computer simulation. It is an operating experimental system. But what makes it unusual is what is flowing through it. Molten salt. The reactor uses a liquid fuel system based on fluoride salts, with the reactor moderated by graphite. The basic idea sounds strange at first. You take salt, you heat it until it becomes liquid. You dissolve the nuclear fuel into that liquid. The fuel salt moves through the reactor core. Fission produces heat. That heat is transferred away from the reactor and can ultimately be used to produce useful energy. The advantage is not that salt is somehow magical. The advantage is the combination of its physical properties and the reactor architecture built around them. Molten salts can operate at very high temperatures without requiring the enormous pressures associated with keeping water liquid at similar temperatures. That means the system can potentially deliver high-temperature heat while operating at much lower pressure, and that creates a completely different engineering philosophy. Instead of designing everything around keeping an extremely hot, pressurized coolant under control, engineers can use a liquid salt system designed to remain stable at high temperature. But there is an even bigger question. Where does the fuel come from? And that brings us to the element that has fascinated nuclear scientists for decades. Thorium. The thorium-gamble thorium is not simply another version of uranium. That distinction matters. The naturally occurring isotope thorium-232 is fertile rather than directly fissile in the same way uranium-235 is. In a suitable nuclear environment, thorium-232 can absorb a neutron and begin a chain of radioactive transformations. Eventually, that pathway can produce uranium-233, and uranium-233 is fissile. In simplified terms, the idea is thorium enters the system. Neutrons interact with it. Thorium is converted through intermediate stages. Uranium-233 is produced. That uranium can then participate in fission and release energy. This is the basic attraction of the thorium fuel cycle. Thorium is relatively abundant in the Earth's crust, and supporters of the technology have long argued that it could provide an alternative resource base for nuclear energy. But there is a reason you do not see thorium reactors powering cities everywhere today. Thorium is not a magic fuel. You still need a reactor capable of managing the nuclear reactions. You need sophisticated fuel chemistry. You need materials that can survive high temperatures and prolonged contact with aggressive molten salts. You need to control radioactive intermediate products. And you need an entire fuel cycle capable of turning the theoretical advantages of thorium into something an industrial system can actually use. That last part is crucial. For decades, thorium has lived in the strange space between scientific promise and commercial reality. The basic nuclear physics is not new. The challenge is engineering. So China's experiment was never simply about building a small reactor. It was about demonstrating whether the entire concept could move another step toward reality. And in 2025, something important happened. The breakthrough inside the reactor. In November 2025, the Chinese Academy of Sciences announced that researchers had achieved what it described as the world's first thorium-to-uranium nuclear fuel conversion in a molten salt reactor. The experiment was conducted at TMSR LF1 after thorium fuel was loaded into the reactor. Researchers obtained experimental data showing that thorium had been converted through the fuel cycle toward uranium, confirming the technical feasibility of thorium utilization in this molten salt reactor system. This is the moment where the story gets interesting. Because the achievement is not simply China built a thorium reactor, the more important statement is China demonstrated the conversion process that the thorium fuel cycle depends on inside an operating molten salt reactor. Think about the sequence. Thorium-232 enters the nuclear environment. It absorbs a neutron. Through radioactive decay, It moves through intermediate material. Eventually, uranium-233 can be produced, and uranium-233 can be used as fissile fuel. That is the fundamental bridge between abundant thorium and usable nuclear energy. Chinese researchers had already operated TMSR LF1 at full power in 2024, and that same year testing with thorium fuel produced evidence of protactinium-233, an intermediate in the thorium-to-uranium conversion pathway. Then came the 2025 announcement of successful thorium-to-uranium conversion. But this is where we need to slow down, because there is a huge difference between proving a nuclear process works and proving that it can power an entire civilization. A 2-megawatt thermal experiment is not a replacement for a power station. It does not prove that thorium electricity will be cheaper than solar. It does not prove that molten salt reactors can be mass-produced. It does not prove that China has solved radioactive waste. And it certainly does not mean the global energy crisis has ended. What it proves is narrower, but it is still important. It demonstrates that one of the critical pieces of the thorium molten salt concept can operate in the real world. And now China wants to find out whether the concept can become much bigger, from experiment to industrial reactor. This is where the story stops being about a laboratory experiment and starts becoming an industrial gamble. The 2-megawatt thermal reactor was never supposed to solve China's electricity demand. Its purpose was to answer engineering questions. Can the materials survive? Can the salt be controlled? Can the reactor operate reliably? Can thorium participate in the fuel cycle? Can engineers manage the chemistry? Can the system be operated safely? And can all of those pieces work together? The next challenge is scale. China has been developing plans for a larger demonstration reactor, based on the same general technology. Documentation associated with the project describes a proposed demonstration system around 60 megawatts thermal, with about 10 megawatts electric output. The purpose is not simply to repeat the experiment at a larger size, but to validate integrated technologies needed for future molten salt systems. That distinction matters. A commercial reactor is not just a bigger research reactor. Scaling nuclear technology creates new problems. Pipes become longer. Heat exchangers become larger. Materials experience more stress. Maintenance becomes more complicated. Fuel chemistry becomes harder to manage. And every component has to work for years, not just long enough to demonstrate an experiment. This is the point where many revolutionary technologies fail. They work beautifully at small scale. Then the real world arrives. Costs rise, materials degrade, maintenance becomes expensive, regulators demand more testing, supply chains become complicated. And suddenly, the technology that looked brilliant in the laboratory has to compete against technologies that have already spent decades building an industrial ecosystem. China knows this. That is why the reactor in the desert is important. It is not the final product. It is the test bed. The question is whether the lessons learned from this tiny machine can be transferred into something large enough to matter. And there is one enormous advantage China has in this particular experiment. It has spent years building the research program instead of trying to invent everything at once. But even that does not guarantee success, because molten salt has a problem of its own, the problem that could kill the dream. The most dangerous mistake would be to hear molten salt reactor and assume the hard part is over. It isn't. In some ways, the hardest engineering work is only beginning. Start with materials. A reactor operating at several hundred degrees Celsius for years is an extremely demanding environment. The molten salt must remain chemically controlled. Metal components exposed to the salt must resist corrosion. Pipes, pumps, valves, heat exchangers, and structural materials all have to survive conditions that ordinary industrial equipment was not designed for. Then there is the fuel chemistry. In a liquid fuel reactor, the fuel is part of the circulating salt. That gives engineers opportunities that solid fuel reactors do not have. But it also means chemistry becomes an essential part of reactor operation. You need to understand what is happening inside the salt. You need to manage impurities and radioactive products. You need systems capable of maintaining the correct chemical conditions. And then comes the economic question. A reactor can be scientifically brilliant and still be commercially useless. If a molten salt reactor costs too much to build, it loses. If maintenance is too difficult, it loses. If regulators require decades of testing, it loses. If the fuel cycle is too complicated, it loses. And if electricity from the finished reactor costs more than competing technologies, Customers will not care how elegant the nuclear physics is. This is why the claim in the title needs to be understood correctly. China has not built a reactor that has already ended the energy crisis. It has built an experimental reactor that is testing a technology that, if successfully scaled, could address some of the problems associated with conventional energy systems. That is a much more defensible claim, and perhaps a more interesting one, because if the technology works at industrial scale, the impact goes far beyond simply producing electricity. What this could mean for the energy system. Imagine a future where nuclear reactors are not limited to one enormous building producing electricity for a distant grid. A high-temperature reactor could potentially provide electricity and industrial heat, and heat is a much bigger part of the global energy system than most people realize. Factories need heat, chemical industries need heat, hydrogen production needs energy, desalination needs energy. Petrochemical and other industrial processes need enormous amounts of thermal energy. China's own description of its molten salt reactor program highlights possible integration with areas including renewable energy, high-temperature thermal storage, hydrogen production, and industrial processes. That creates an interesting possibility. Instead of thinking about nuclear power as simply reactor electricity grid, you could eventually think of it as reactor electricity plus industrial heat, plus energy storage, plus other applications storage. And that could make the technology more flexible. There is also the resource question. If the thorium fuel cycle can be developed into a practical system, countries could gain another route toward nuclear fuel security. China has particular strategic interest in this area, because researchers have linked the technology to the country's broader thorium resources. But again, the word that matters is if. Thorium does not automatically make nuclear energy cheap. It does not automatically eliminate waste. It does not automatically make reactors safer. And it does not automatically solve the economics of nuclear power. Those are engineering and industrial questions that still have to be answered. But there is one reason this deserves attention. China is not merely discussing thorium. It is operating a reactor designed to investigate it. And that puts the country in a very different position from someone publishing another theoretical paper about what thorium might do someday. The real energy race. There is a larger story hiding underneath this reactor. For decades, the nuclear industry largely followed one dominant path. Large reactors, solid fuel, water cooling, huge infrastructure, massive upfront investment. That system produced enormous amounts of electricity around the world. But now several countries are exploring alternatives. Small modular reactors, advanced reactors, molten salt systems, fast reactors, different fuel cycles, different cooling systems, different ways of producing and using nuclear heat. The race is no longer simply about who can build the biggest reactor. It is becoming a race over which reactor architecture can survive the transition from laboratory to mass deployment. And China has a particular advantage in one part of that race. It is willing to run long-term strategic research programs and build physical demonstration facilities. The TMSR program began as a major Chinese research effort more than a decade ago. The result is now sitting in the Gobi region, producing real experimental data. That does not mean China will automatically win. Nuclear history is full of technologies that looked promising and never became commercially dominant. The United States operated an experimental molten salt reactor at Oak Ridge in the 1960s. Scientists have been discussing thorium for generations. The idea is not new. What is new is the combination of modern materials science, advanced computing, China's industrial capacity, and a sustained effort to demonstrate the technology. That combination is what makes the current moment worth watching. Because the question is no longer, could a thorium molten salt reactor work in theory? China has moved the question forward. Now it is, can this work reliably, economically, and at a scale large enough to matter? And that is a much harder question. So there are 3 things to watch. First, watch the larger demonstration program. The next generation of the technology has to prove that the lessons from the 2-megawatt thermal experiment can survive a much larger industrial system. Second, watch the fuel cycle. The thorium-to-uranium conversion breakthrough is significant, but the complete fuel cycle has to become practical, reliable, and economically manageable. Third, watch the economics. This may ultimately decide everything. If China can build these reactors faster, cheaper, and more reliably than competing nuclear technologies, the story changes dramatically. If it cannot, The reactor may remain an important scientific achievement without becoming an energy revolution. And that brings us back to the tiny machine in the desert. It is easy to look at a 2-megawatt experimental reactor and dismiss it because it is far too small to solve a global energy problem. But that misses the point. The first computer did not run the modern internet. The first aircraft did not carry hundreds of passengers across oceans. The first experimental nuclear reactors did not power entire cities. Technology begins with proof. Then comes scale, then economics, then deployment. China is somewhere in the middle of that journey. And the most important thing about TMSR LF1 is not how much electricity it produces today. It is what its operators are trying to prove for tomorrow. A nuclear reactor that uses molten salt, a fuel cycle involving thorium, a system capable of operating at high temperatures without relying on the same high-pressure architecture as conventional reactors, and a country trying to turn all of that into an industrial technology. So, has China built a reactor that can end the energy crisis? No, not yet. But it may have built something more important for the moment, a working experiment that could determine whether a radically different kind of nuclear power deserves a place in the world's energy future. And if China can take this small reactor in the Gobi Desert and turn its experimental success into a reliable, economical, commercial system, the consequences could extend far beyond China, because the biggest energy breakthrough may not come from discovering a completely new source of energy. It may come from finding a better way to use nuclear energy we already understand, and that is why the little reactor in the desert is worth watching. The machine is small, the experiment is not. The question now is whether China can make it big enough to change the world.